Hey guys, so as promised yesterday, we're going to be walking through the malware code that I utilized in the first malware lesson. Okay, and so this malware. So let me kind of give you an idea of what I'm trying to do with this series. Okay, the idea here is going to be we're going to take this malware and we're going to evolve it. Okay, and at the same time, as we evolve the malware, I am going to show the defender techniques needed to solve these problems that this more advanced malware presents. Right? That's the idea, because usually when I see people teaching this stuff, they focus on one or the other, and they use existing malware, something that already is sigged, fingerprinted. This is about having a brand new piece of malware, and what are you supposed to do with it? How are you supposed to create it and evolve it for the attackers? But at the same time, as a defender, okay, well, this is what the attackers are doing. What do I need to do to mitigate that? Right? That's the whole idea here behind this series. Okay, so let's get into this. Okay, so the high level structure of the application, right? So what we're going to do is so the application is here, right? And so you'll see that we're just going to start at the top and we're just going to go down to the bottom. And I'm going to walk you through each chunk, what each chunk is doing and why. Okay, it's going to be a thorough walkthrough. And then I will post that on GitHub for you guys to bring down and do whatever you want to with it. And I'll also post two versions. I'll post one that's heavily commented, and I will post one that's clean. And I will also post these notes. All right, so the high level structure, the shape of the application. Okay, so it runs forever, it's on a timer, it probes sensitive files, it builds a structured report, and it communicates with the C2 server, right? It closes connections immediately, and it leaves behind minimal but useful host artifacts. Okay, this was done purposefully for the defender side, okay, to be able to show certain defender techniques. There's certain things that the malware does right now that we will eliminate to basically make it harder and to show those more advanced defense techniques that you'll need to use to catch this stuff. Okay, so the first thing we do is define our constants. Okay, these hard code these constants hard code where local artifacts go, right, and where the network traffic goes, right. So this is our C2 server right here, right. So why are we doing this? Like, why? So at first glance, I'm sure some of y'all, you're like, oh, you shouldn't hard code. You should be professional. You should do is the environment. You configuration file. It's like, wouldn't a real attacker make a configuration file? It's like, bro, sometimes, right? But often they don't, especially early on, like we are right now. Okay, most malware, it doesn't start as like this polished framework. It's a POC. It's tailored for a single campaign, and it's targeted, right? It's very targeted. You want to prove, like when I've done this for realsies in the past, man, I I would often test this stuff on some very low risk licks before I would expand it out, just to see if it would work outside of my controlled environment. Okay, that's the way to do it, so you don't waste a bunch of time. Okay. Um, and also, it's very common when the attacker controls the payload and the C2 server. Like, dude, why make that configurable? It's like, bro, I know the C2 server configure, I know the C2 server IP address. Why do I need to make it configurable? Right? And also, many real world intrusion tools, they're really not meant to be used broadly. They are very much focused on the campaign at hand. And honestly, you need to be careful with that. You need to be careful with reuse, because um, you every time you do something, man, it needs to be a little different. You need to change things up a little bit. If you just do it the same way every time, you're gonna get caught. Okay. Um, and so also you need to consider that every additional configuration mechanism, it adds code complexity, it adds potential bugs, it leaves things on disk, and it more things that defenders can just find. And so with hard coding constants, you get that single binary, you get no config files, no environment variables, there's no command line arguments, there's just fewer moving parts. And this is kind of a counter forensics move, right? Because fewer moving parts means fewer observable artifacts that defenders can get their hands on. Let me tell you, I have seen my own and many others. Most of the malware that I see that fails out there is because of some stupid configuration issue, right? There's a broken path. There's an environment. There's something up in the environment you didn't account for. Incorrect runtime arguments, missing config files, like all kinds of things. So you should always prefer predictability over flexibility. Guys, like this is like I'm sorry guys, but when will you learn, right? You need to think like a criminal, not a corporate software engineer. Okay, that's what this is about. Okay, let me tell you, most people get caught because they're out there thinking, oh, I'm just a computer guy. It's like, no, dude, by the law, you're a crook, and so it doesn't matter if you steal that money and give it all away. It doesn't matter. You're gonna get arrested. You're gonna go to jail. Okay, so just think about that. All right, now, right. So the defender takeaway for this, right? They do. Hard constants do help out defenders. They're strong indicators of intent. They're excellent pivot points in forensic analysis, and they're often reused, like I said, across multiple infections. They like these constants because they appear in memory, they're in binaries, they're network traffic, etc. Right? And reverse engineers pay very close attention, and they look for these constants. And as with anything, the method that you choose depends on your lick, right? And we'll continue to build out this code in the future to show various configuration methods and further obfuscation techniques. Okay, and so the targets. So this defines a list of high-value paths, right? These aren't just random. They represent privilege, escalation, credential access, and persistence opportunities. Okay, now you don't go into a system and you just scan it blindly, everything, right? Because that creates a lot of noise. You want a playbook, right? The idea is to probe choke points. And so, as a defender, when you see processes touching these files, the intent's pretty obvious, and you got those false positives drop dramatically. And this is where those tools like Audit D, like I showed yesterday, really shine. Okay, now timestamps. So this is important. This function looks like, okay, what's the big deal? But this is the coordinator, right? This enables coordination, and this is what turns these isolated infections into campaigns. Okay, because so this is done for C2 servers. Okay, so C2 servers need ordering to be able to correlate multiple hosts. Okay, because usually you're probably going to be controlling multiple environments, and so you need to know like the order of things. Okay, because without timestamps, you're not going to know when events happen based on command. You're going to be left wondering if a host is active. You're going to be wondering if if a report is fresh. It's about context, right? It's not necessarily just about metadata. And so when you do control multiple boxes, you want to know which machines are vulnerable, which ones are responding, and which ones are worth further escalating. And so they let attackers correlate that activity across hosts, identify common behavior windows, and detect which infections are alive versus dead. And this is obviously very important for distributed campaigns. So this is just more about timing. And so the defender takeaway here is, timestamps, they let defenders detect beacon intervals, right? It allows timing analysis and correlation across telemetry sources. Okay, and so now let's get into the local logging function. Okay, so open options, right? So this explicitly creates or appends, it doesn't truncate, and it leaves a minimal trace. Now, unwrap. Okay, now this crashes loudly if the logging fails, and so there's no silent failure. Now, why? Now you're probably asking yourself, why would an attacker allow crashes? Right? This isn't production malware behavior. Remember, we are in the early stages of the application, right? Development, testing, early deployment, and controlled campaigns. So in these phases, I'm more concerned about knowing something failed, identify why it failed, and avoiding silent misbehavior. Okay, silent failures can be dangerous because if logging fails silently, you're going to get incomplete reports. You get weird behavior, and then it's also going to be harder for you to debug the thing. Crashing loud means the failure is obvious, the problem is noticed, and you can fix the issue. This is realistic in context, right? Because many malware families, they start noisy and become quieter over time, and logging is removed in later variants, right? So I'm once again, I'm attempting to simulate the realistic creation of a piece of malware, right? While providing defender techniques in parallel as the malware evolves. And this also, this also mirrors legitimate software development, right? The whole agile thing. You fail early, right? You get that thing out there, and then you kind of let the public tell you what's wrong with it, and you enhance it from there. So the defender takeaways here. Obviously, early stage malware is going to be more brittle. It's going to leave artifacts. And obviously, this is very useful for defenders, right? Because it just gives them just more artifacts to analyze. And so later in this course, we're going to replace unwrap with proper error handling. We're going to suppress crashes, and we're going to show how defenders lose that visibility, right, as the malware matures. And like I said, this evolution is part of this series. All right, now the report struct. Okay, this is a very important design choice. Okay, because here what we're doing is we're doing in-memory collection versus disk logs. All right, and so the current state of the application collects findings in memory, it builds a structured report, and then sends it directly to the C2 server. It never writes those findings to disk. Okay, this is intentional. Most modern malware, they do not write sensitive data to disk. Right, and it it stages data only briefly in memory, and then exfiltrates that, and exfiltration is directly from memory. Right, we do this because of the artifacts. Right, and memory is ephemeral. Reboot clears evidence. Right, it's these file-based indicators of compromise that's what you want to avoid. Right, because those are very powerful for defenders. And so by keeping everything in memory, the host has fewer artifacts, and defenders have to rely on behavior, right? Like we saw yesterday, right? When we ran ClamAV against the custom malware, it didn't detect anything because there's no signature. It's all behavioral based, right? So when defenders focus only on files on disk, antivirus scans, and static indicators, they miss malware that lives in memory, okay? Yeah. Now, the probe targets function. So this is the privilege escalation intent. Okay, so here, this is pretty straightforward, guys. We loop over the targets, and then we do a read attempt. So this is kind of where if you were going to inject an actual exploit, this is where it would be. So right here, though, we're just asking a question, right? We're just seeing if we have access, if the file exists, etc., right? And then we do a write attempt, and then we record the findings, right? Very straightforward here. Attackers, we don't need success immediately. We need situational awareness, right? We need to know what's there. And then the defender takeaway: repeated failure is not noise. Repeated failure is recon, right? Like we showed with the audit D, right? That audit D log yesterday was huge because this thing is beaconing every 20 seconds, right? So, yeah. Now, the send beacon. Okay, so once again, very straightforward, right? We do JSON serialization, right? The entire observation set becomes portable, compact, and parsable. Then we have the C2, right? HTTP, outbound, short-lived, blends with normal traffic, and then the connection opens, sends, closes, and there's no persistence, right? So the defender takeaway. So, right, this explains why SS didn't show anything yesterday, right? Why packet capturing works and why timing matters, right? Because remember, yesterday with SS, we couldn't catch the beacon, right? Now, in main, this is where the orchestration and persistence happens, right? We enable the audit D correlation, proc inspection, and incident timelines. This is where we write the local log, and then we go into the infinite loop. And then, so this models persistence without startup hooks, cron services yet, right? Yeah, and then we have feature gated behavior, right? So we have compile time capability selection. So this means as we build this thing out, we can use different feature flags to offer different malware variants, right, and make this thing into more of a platform. And then we have our sleep interval for our beacon. And okay, so and then so why is this code realistic? So even though this is currently a benign application, it hides implausible paths, it probes sensitive targets, it exfiltrates structured data, it beacons briefly, and it leaves minimal residue. All right, so nothing in this code is advanced, and that's what makes it good. Okay, how ordinary it is. Malware is not magic, mystery, or fear. It's mechanics, method, and understanding. All right, and we're going to be evolving this malware throughout the series. And I'll be providing those defensive techniques along the way to solve for these evolved versions of the malware. So for the malware, we're going to be removing logging entirely, implementing adaptive beaconing. We're going to move to condition-based probing. We're going to use stage exfiltration. We're going to implement various persistent mechanisms. We're going to be enabling configuration to come from the C2 server. We're going to fix that crash behavior. We're going to start doing more obfuscation techniques in general, and more, right? By the time that this course is done, you should have a really good grasp about all of these techniques that malware uses, okay? And so each enhancement, it's going to improve attacker stealth, reduce defender visibility, and require better and more advanced defensive techniques. This reinforces the core idea behind this series, right? Attack and defense co-evolve. The idea here is to give you guys to let you guys learn why attackers make trade-offs, how those trade-offs create detection opportunities, and how defenders have to adapt over time. Okay. Remember now, because malware is not dangerous because it's clever. It's dangerous because it's deliberate, right? And that's what this is going to be. This is going to be real-world stuff. All right. All right, guys. That's going to be it for this one. Like I said, I'm going to be posting the code up to GitHub. I'll be posting one with comments, one that is clean. Let me know if you have any questions about this stuff. Help each other in the comments. Ask those respectable questions, get respectable answers. And next week is Christmas, guys, so I'm not going to be around, but I do have some stuff that I will be doing behind the scenes next week. And so, yeah, got some cool stuff coming up. All right, guys. Well, have a good, safe holiday. Enjoy time with family and friends, and I'll see you when you get back. All right, guys.